Welcome back to another episode of Brain Buzz Podcast. This is our obviously first episode. You aren't used to seeing my dumb mug all the time, but get used to it. For the next hour or so, you're going to see Kyle and I, and then our guest Adam Fortais, who is a physics student at McMaster University who specializes in soft matter material and fibers. So he shows us a bunch of cool demos. We really enjoyed using video to highlight his work because it was perfect for it. And let us know if you really enjoy this format or if you like seeing video of us talking. Editing's really rough. I'm going to continue to work on my editing skills when it comes to video podcasts. But we do hope you enjoyed the episode, and here's the intro.
Welcome back to another episode of Brain Buzz. We are your hosts. I'm Kyle.
And I'm Drake.
And today we are joined by instructional assistant, co-host of Alma Mac podcast, physicist, all-around cool dude, Adam Fortais. Welcome to the program, Adam.
Hi, thanks for having me. It's great to be here.
We're excited to have you on board. First and foremost, did I hit all of the appropriate pieces there? Did I miss anything in that intro?
No, I think that's the gist. I'm quite into karaoke as well. You could add that if you'd like.
Okay. Singer.
Yeah, that's about it.
We didn't see that on your profile. There's a lot of things on your profile to go through here. Adam, we don't usually have physicists on, so this is gonna be really fun. You specialize in soft matter. That's like what you described to me. I left it to you to describe. What do you do? What's the kind of work that you work on in physics?
Yeah. So So maybe I'll start even a little bit further back. Physics, there's theory. You got your experiments. Basically, any bit of physics that you want to do has both of those. So I'm an experimentalist by trade, but soft matter in particular. So soft, we know that word, squishy things and whatnot. In a sciencey way, usually soft, we're referring to things that you would see every day, like biological materials like skin or plastics and rubbers also count as soft. We also include liquids. What we're ruling out and like what we're excluding are hard things like crystals, a lot of electronics we generally aren't really concerned with in soft matter. Yeah, I think I feel like it's stuff that you can kind of understand on a day-to-day basis, like silly putties and shampoo. And I'm personally very concerned with material properties and what happens to objects when you apply different forces to them. And they do also, from living in the world, when you interact with certain things, depending on what they're made of and what their shapes are, they're going to respond differently. So broad strokes, that's kind of what I study. My lab is I'm in a kind of a cool space with my lab. We don't really have any specific research question, which I'm not sure if that's a new concept to you guys based on your field, but we're kind of just an exploratory group. We go into the lab, we have materials, and we have some techniques that we're pretty good at, making certain types of samples, and then we kind of just play around with them. See if they do anything unexpected. If we can't explain it, then that's a project. If we can explain it, then we keep messing around. And then afterwards, we kind of try to make these connections between what we saw and either technology applications or biological connections. So yeah, that's probably a lot to hear without any sort of hard examples or soft examples.
Yeah, you only use soft examples in your work, so we won't go through hard examples. Okay, cool. So Adam,
let's talk about these soft examples then, maybe, because you just mentioned pretty much everything under the moon except for electronics and what was it, crystals. I mean, we use electronics all the time, but like what kind of soft matter stuff are you looking at, and like what are you really testing within those? Like you say you're playing around with them a lot. What are you testing? Like their breaking points, like what you can use them for? What are you doing?
Yeah. So let's see. The kind of stuff that I'm really interested in, I think you could probably say is in the realm of like pattern formation. And so places where you might see interesting patterns form in the soft matter world is like wrinkling of skin. So if you furrow your brow a little bit, you can see sort of a wavelength popping out. So somebody like me might ask, why are my wrinkles spaced apart that way? Why
Right.
are they not, thinner or shorter or, more wavy? What properties cause them to be that specific pattern? Turns out it's the thickness of the skin, the stiffness of the skin, the stretchiness of it. So in the lab, what we can do is we can make these, very thin, elasticy films that are similar to skin, and then, play with different things, play with the stiffness, play with the thickness of it, and then apply different compressions and stresses and see how that wrinkling pattern changes.
Right.
We can make mathy predictions to say, like, based on these combination of variables, stiffness, thickness, length, width, etc., I think that we're going to get these kind of wrinkles, like really small wrinkles. Or I think that, if we make it thicker or something, we're going to have these big cascading wrinkles.
Right.
And so that's one of the types of experiments that has gone on in our lab. I've been playing with fibers, though. Similar idea, still elastic materials, stretchy, potentially bendy. But I've been looking more at like what happens if you start with like a fiber and you compress it. That's kind of like a wrinkle, like a 1D wrinkle. So that's pretty good.
Yeah.
But then you can do all sorts of weird stuff, like you start and compress it, and then you get this loop forming. It's kind of like a 2D wrinkle in a sense. And then you can get, almost arbitrarily complicated. I had a spring here. I don't know. I'll show you the spring a little bit later. But
Yeah.
yeah, I've been playing with fibers, different thicknesses, stiffnesses, elasticities, and just messing around with them.
And so what is it? What is a fiber per se? What's the definition of a fiber?
Yeah, fibers, the way that I use the term fiber, it has to be, the fibers I use are cylindrical. So
Okay.
they have a circular cross section. They're going to be a lot longer than they are wide.
Mhm.
So if you think of like a tree trunk, that's not quite a fiber. It's pretty thick. It's of the right shape for the most part, but it's a little bit too thick per length. So
Right.
I'm looking at, it's got to be a slender object.
Like a hair,
So
like a
yeah,
someone's
hair
hair.
is a perfect example.
Yeah.
In my world, like this is like a broom bristle. Yeah, I could consider this a fiber. It's pretty brittle. A lot of fibers that I work with are elastic, so they don't snap. This one
Right.
can snap, but that could be a fiber. If we zoom down into smaller scales, like a flagella on a bacteria, we can
Ah.
treat that kind of like a fiber, depending
Okay.
on what you're doing with it.
Mhm.
And that's the kind of thing that gets me really excited when you start to apply these like very basic concepts, like fibers, geometric concepts.
Mhm.
Like we have this cross section, we do this thing to it, and it behaves this way. And then looking to nature and saying, okay, flagella looks kind of like a fiber. Does it behave like what I've been doing in the lab with my experiments?
Mhm.
Turns out a lot of cases, yes. DNA ends up working a lot like that. So the way that it bends and twists and conforms into different shapes and stuff, we can model that behavior with some of our experiments on like these larger scales. Of course, these analogies break down at certain places.
Yeah.
So that's another thing that we like to explore is how similar are these biological things to the stuff that I play with in the lab?
Right. Yeah, totally. So just really quick, can you confirm for us what a flagella is?
Yeah, they come in different shapes and sizes and styles and whatnot. But little bacteria floating around in your body somewhere. It's got to move around somehow.
Mhm.
So nature has come up with all sorts of different ways of doing it. But this one is basically a tail that comes off it. You can think like a tadpole or something like that, and then that tail sort of whips around and it uses that as a little motor.
Right.
Right. Okay,
Yeah.
so it propels us along.
Yeah.
Cool. Go ahead,
So
Drake.
I have a question for you,
It's to
Adam.
you.
This is kind of, I haven't done physics since it would have been grade 11. So it's been over 12 years, and um, I'm interested in kind of what got you into physics and got you asking these questions specifically. So why are you looking at what got you interested in fibers, I guess, or was it just kind of like that was what your lab was working on? You're like, okay, I'll do fibers, or was it like was there a tangible reason why you're like, I want to look at fibers specifically?
Ever since I was in elementary school, I've just been fascinated with fibers. No, I'm just kidding. I started off in probably high school getting just interested in physics because of these like pop science books, like Brief History of Time and all this, exotic theoretical stuff, cosmology and all that. I thought that was really neat. Um, I had very little direction coming out of high school, and I thought, well, that's an area that I can go into. My grades are good enough, and I think it's kind of cool, so let's check it out. So signed up for physics undergrad and, started off thinking I'd be, cosmologist or string theory guy or high energy something or other. Then sort of switched my mind. Maybe I'll do astronomy, maybe I'll do planetary science. Um, Changed my mind again. Just anytime I saw like a new field, the closer I got to a field, the more I just wanted to do that thing. I think I was just, excited by whatever I was being shown. It was like,
Yeah.
so I ended up in a polymer physics lab as a internship in undergrad. So I was working with rubbers they make tire inner liners like for cars, but they
Okay.
also do like the base of shoes and things like this.
Hmm.
So that's probably the first time I really saw soft matter in like a really experimental setting.
Right.
So we were doing all sorts of material properties like based on the polymers that we put into the mixture, how does it bend, how does it flex, all this sort of stuff. So that
Right.
was kind of my first little bit foray into soft matter. That turned into a thesis project trying to develop a fluid that's very much like blood but isn't blood for doing experiments.
Mm.
Okay.
Um, and I was surprised to see that that was actually the same field. A lot of the same physics concepts, a lot of the same math. They can be, translated. It's all very much material properties, and I apply a force to a thing, and it, reacts in a certain way. So
Hmm.
a lot of overlap there.
Yeah.
Um, and then for grad school, I didn't know if I was going to get into grad school. I applied to a bunch of places, just random programs, basically. My grades weren't super hot, but found a supervisor who didn't actually look at my grades and took me on because, I don't know, he's a good guy, I guess. I don't know. We had
It's
like an interview and
altruistic.
we sort of hit it off. We both like bikes, so that seemed to work out all right.
Yeah.
He obviously thought you were a good guy too. So,
Yeah, I think I just showed excitement, and he likes excitement. I think
Yeah.
he would be fine with that characterization of me. And yeah, and like I said, his lab was very much an exploratory place. He very much started in polymer physics, like just looking at different types of rubbers and plastics and how they behave at different temperatures and things. And you start doing a project with him, and if it doesn't work out, usually you'll see something cool in the microscope when you look at your sample. And if you can't explain it, then he tells you, well, you have a new project. You have to explain that now.
Hmm.
And yeah, things just sort of like cascaded, and we started playing with films and deforming them. And then we realized by accident we could make these really nice fibers. Um, that's actually its own little story.
Yeah, let's go to it. Yeah. I
yeah,
mean,
It's
let's hear
like
it.
we're
a
definitely
jump
going to
off.
have a segment with you showing these things too, because we're really stoked. We're really stoked just to have this video podcast with you, just because you can show us this, and it's one of there's a few times that we've had like guests on where like we really need video to do it justice. So I'm excited to have this and have you demonstrating as well.
Yeah, so maybe all I'll say about the fiber making is that I'm going to show you some demos, and they're going to be, roughly tabletop size, like the size of, you can see it, obviously. But the fibers that I make are about 10 times thinner than your hair. So they're very, very thin. And the reason we do this is kind of something we do in the lab in general. We go to thin and small and very light so that we can ignore things like gravity. So
Okay.
you can imagine, like, if I am playing with this elastic band and I want to see how it deforms, every time I compress it, it deforms downward because gravity's pulling it down.
Mm-hmm.
If we were in space and I pushed it inwards, it could equally go upwards or downwards.
Okay.
So we go very thin, very small to get rid of those kind of effects. So we can just focus on the compressions.
Oh, that makes sense. Yeah.
Yeah, so we, have this technique that is identical to how people make cotton candy floss. We just heat up a polymer, stick a little pipette in it, and yank it out, and we get these perfectly cylindrical, uniform fibers. And then we mess around with them. We twist them, we bend them, we stretch them.
Wicked.
Yeah, so maybe I can tell you a little bit about the types of forces and deformations and
Yeah.
Yeah, let's
So
do it.
you talking about these kind of like not necessarily microscopic, but very small fibers, right? And you're saying that gravity's not affecting them as much. Why is that? I mean, as someone that doesn't know anything about physics, and I know I have to accept the fact that the gravity is a real thing.
yeah.
Why is it not affecting them as much?
So maybe it's easier to explain this in the context of like of liquids or something. So
Sure.
when you're looking at like a liquid droplet, you can imagine if there's no gravity and it's sitting on like a surface, you get this nice like spherical cap. Like a perfect droplet is going to be a sphere in space. And so if it's sitting on a surface, it's going to be sort of like just a cutoff of a circle. That shape is because of surface tension or a specific type of tension that the liquid has. And so that has a certain, like the force of that has a certain magnitude. It's small, but it's there. And as you go bigger, the magnitude of that force scales with the area. Similar for stretching like a film or something like that. If you want to stretch it, if the area is small, it's going to be easy to stretch it. If you make the area bigger, it's harder to stretch it.
Okay.
So those kind of forces scale with the area of an object. So if you think of like the area of a rectangle, it's length times width.
Right. I remember
Gravity,
that.
though,
That's about all I
gravity,
remember.
though, is one that it scales with the mass of the thing, which is more related to the volume.
Okay.
So the volume now is going to be like length times width times height.
Mhm.
So now if you change one of the dimensions, the area is going to get bigger, but only by a certain amount. The volume is going to get bigger, but by a lot more.
Okay.
Right.
Right.
That
Because you're
kind of
trying to
makes
get by
sense?
3 opposed to 2, right? More or
Yeah.
less. Yeah. Yeah.
So
Okay.
now if we say that the force of gravity is related to the volume,
Yeah.
and the tension or elasticity is related to the area,
Okay.
and we start scaling these things down,
Mhm.
uh, the volume one, the cubed one, the gravity one, is going to change a lot faster than the other one.
Okay. Okay, so the size is really like by reducing the size, you're reducing the amount, the effect that gravity will have on it, and you're looking specifically at the volume. So the smaller the volume, the less effect that gravity will have on it. Cool.
Yeah, yeah.
Cool. Okay.
That was a beautiful way of doing it. I mean,
Yeah.
physics is hard. Was it hard for me in grade 11? But you're making it sound quite easy, so I appreciate that, Adam.
Okay, that's my job. I'm
And you're doing,
glad you
yeah.
said that.
You are. I mean, yeah. It would be pretty bad if you weren't, because your whole career is basically built on science communication and effectively explaining things. So you're doing a really good job. I appreciate it. I respect the craft.
Thank you.
I,
Thank
I
you.
wish my grade 11 physics teacher was as eloquent.
I could just show you like a formula sheet if you'd prefer.
No, that's okay.
When you have a question, I'll point to the relevant formula.
Yeah,
Oh,
just get the
God.
textbooks out. Yeah, no, I'm okay with no physics textbooks.
Yeah.
So Adam, I'm kind of curious, talking about this, and we'll have you. I mean, we'll probably insert some of these demonstrations as well. But I'm curious, what do you what's the not necessarily what's the point, but what's the goal of doing this research? I'm thinking in my head when you were talking about like, sneaker rubber and things like that and tension, I'm thinking, okay, there's relevance here for, products or other things that we use to see how durable they are or what kind of tension they can be under before they, break. But what are your kind of implications that you're kind of working towards here? What's the real goal of this work other than theoretical?
Yeah, so my lab, while being an experimental lab, is really far removed from like a marketable product. Um, so to say that, the thing that I'm working on, that my thesis is on, is going to go into a certain product is difficult, or like understanding a specific thing in nature, like DNA,
Yeah.
is a little bit difficult. But what I can say is that I think the thing that connects all of my projects is trying to take something that's very complicated, like the way that DNA folds or the way the flagella works or something like this, and reducing the number of basically making it as simple as possible. See, like, how many things can we take away while still reproducing, similar behavior that we see in nature.
Mhm.
And the reason we would want to do that is, um, say I want to make a tiny bacterial robot, like a little robot that's the size of bacteria that uses a flagella to move around and stuff. Could be a cool, drug delivery mechanism or something. But I don't want to, evolution worked for millions of years to make that flagella.
Mhm.
So I don't want to have to go in and, re-engineer every aspect of that. I want to see what kind of stuff I can get out of the equations, what kind of stuff doesn't matter, and then be left with just the stuff that does.
Right.
And hopefully we can use that kind of stuff to, create predictive, relationships, things that could allow engineers to create something new. Are you familiar with like it's called Hooke's law, but it's the basically the relation between, stretching a spring and the force it takes to stretch the spring, like how
I'm not familiar with Hooke's
It's
law.
been a
No.
while, Adam. I don't know if they actually even taught me that in grade 11. So could you explain Hooke's law? It sounds like intuitive from what you explained, but
how about friction? Friction, I think it might be a better one.
okay.
Do
I
you
have heard
remember?
of friction, so that's good.
Yeah, so basically if you want to know the force of friction, all you need to know is the mass of the object and its friction coefficient, which is just this number that relates how much mass the object has, like how much weight it has on the surface,
Okay.
and how much basically frictional force you're going to get when you pull the thing.
Okay.
So that's kind of the simplest equation that you're going to see. There's like three things involved, one equal sign, but it turns out friction is like super complicated. If you look microscopically, like the smoothest thing has all of these different ridges and bumps and things. And what friction is the bumps on one object interacting with the bumps on the other object, and then sort of grinding and like moving past each other. Turns out it's way, way more complicated than this very simple equation would suggest.
Mhm.
I'm kind of concerned with. I start with looking at all the bumps and ridges and things like that, and I want to end up at the very simple equation.
Right.
Right.
So
Okay.
yeah, what kind of stuff can I throw out?
Yeah. Yeah, for sure.
That makes sense. So, but you've whet my appetite now. What is Hooke's law? Can you explain it? Is it simple? Is it simple enough that even a dummy like myself can get this? Or
I think you can do this.
okay, let's
Okay.
do it.
So we start with an elastic band. It has a what we call a natural length. So that's just the length between my fingers.
Yeah.
Okay.
We'll call that, L or something.
Mhm.
Um, so this is like a spring. This elastic band is much like a spring in that if you apply force, you can stretch it, and now it has a new length, right?
Right.
Right.
So if this is the original unstretched length, no force, we apply force, I can double the length. I can continue stretching it, and the force required to keep stretching it is linearly proportional to the change in length. So if I double the length, it takes a certain force. If I make the length 4 times bigger than the natural length, it's only going to take twice as much force to do that.
Right.
So every time,
yeah, you call
yeah,
it like, what would you call that force? What's the force of what's the words that you guys use to do that? I'm like, say you gave it 2 force and then you gave it 4 force. Like I know that's not the right terminology.
yeah. So this is where the day-to-day intuition actually comes in. The force right there to stretch it, that's
Yeah.
just tension.
Right.
That's what we call tension. A rope can have tension.
Mhm.
And even something that doesn't stretch, like this straw from a broom, I can apply forces and try to stretch it. It's under tension just like the elastic band,
Right.
but because of its material properties, it doesn't stretch nearly as much.
Yeah.
It can stretch a little bit. You can't really see it. Can you see it?
Yeah.
Yeah. Yeah. I can't see the tension. I can't see the tension changing anything though.
Yeah, so that's basically exactly one of the things that I could be studying. So thickness wise, these are pretty much similar,
Mhm.
but I can apply, a tension to both of them, and they do drastically different things.
Right.
Alternatively, if I want to compress them,
Mhm. They'll also
they'll,
see different properties, right?
yeah, you'll
Yeah.
get different types of bends. This one might shatter. This one will do all sorts of stuff like that.
Right.
But yeah, Hooke's law just tells you basically how much it's going to stretch based on how much force or tension you've applied to it.
Wicked. Yeah, that's really
Thank
cool.
you.
So
Yeah.
I think so in your work, and so the work that you're doing is much more at like you said, a smaller scale because you're looking at specific things that are microscopic like sizes, right?
Yeah.
I think
Do you
that's
ever
really cool.
do you ever lose the polymers in the lab or the the fibers?
Oh yeah.
I would imagine so. Like, oh
So
shit, where did I put that?
I'm hashtag blessed that I have pretty good eyesight. So when I pull these things, they're usually connected like to the pipette on one end, but then the other end sort of floats around. And I kind of, I sometimes bring the pipette into the sun a little bit to get like a glint off of it,
Okay.
so I can sort of see where the very thin thread is. But that is a real issue for some people in the lab. If it's if you don't have like the operation board hands, some projects are just going to be too tough for you, so you have to try something else. If you
Oh
have a lot
wow.
of trouble seeing the polymer thread, you might have to do a different project. Like there's a lot of like little stuff like that
So
can be very difficult.
the two of us wearing glasses maybe not the best industry in that sense.
Maybe you're perfectly honed though. Maybe.
Yeah,
Oh,
who
true.
knows? Yeah. I can barely see the words on a page, so I think I'll pass on the microfibers. But I think that's really interesting. I kind of want to ask as well, Adam, because everybody in psychology doesn't really there's a lot of differences in what psychology labs look like and physics labs look like and chemistry and biology and things like that. So when you're in the lab, what kind of materials are you using? You said you're extracting the polymers, but what else are you using? What kind of things are you using on a daily basis?
Yeah. So I think our lab is kind of like if you ever played with Legos or Connects as a kid, it's kind of like the ideal situation if you enjoyed it at least. We
Sounds like
have
my
like a
dream.
couple. We have like a couple things that kind of happen in or that we use in all of our experiments, like microscopes. The polymers themselves are just chemicals that come in a jar. They're usually flakes or something like that. But otherwise, we kind of just build whatever we need to build to get our experiments done. So one guy in our lab, I haven't been back in the lab in a while.
Right.
I have not a huge need to go there, and with COVID restrictions, it's like very much like sign in, sign out kind of thing.
Yeah.
For one guy who has been in the lab, he built a spin coater. So if you want to make very thin polymer films, there's this technique you can do. You dissolve your plastic in something like nail polish remover or paint thinner. So then you get something very much like a paint, plastic suspended in a fluid,
Mhm.
and you can either you can paint it onto things to make a thin film, but a really nice way to make ultra thin ones that are ultra uniform is to put the thing you want to put your film on basically a record player, a
Okay.
turntable that
Yeah.
spins really, really fast. And then you do a little tiny drop on there, and it shoots all this extra fluid out, and it leaves behind this really nice thin film. So we've built things like this. In my case, I've built the lamest robot of all time. You clamp your fiber in two spots, and then one side stays fixed, and the other side does this,
Nice.
and sometimes it does this. And then there's a microscope looking down. But
Right.
yeah,
That's a
there's all
smart
sorts of
robot. At least it has two functions. It's not just one function.
Yeah, yeah.
beep boop. Yeah, it's pretty cool.
It's kind of neat. Like that's something I've always admired about other like physics labs, especially is and engineering labs and other of that ilk is there's that hands-on, really like like hands dirty kind of science where you're building stuff and you're doing like this cool stuff. I think I mean obviously there are exceptions in psych, but a lot of it is sit in front of this computer and answer this question. So I mean maybe there's a little bit of a different coding element in a psych lab, but I like the idea of like you said earlier this like Lego like
Yeah,
Lego lab on steroids essentially.
Mhm.
It's kind of
Yeah,
cool.
it's almost like a playground. It sounds like it's nice.
Yeah.
So Adam, I mean, it's been really interesting talking about this, and I'm stoked about the all of the demos and stuff like that. I'm curious with physics. We always ask this for all our guests, so I'm curious what you have to say. I'm sure there are. What kind of myths and misconceptions are there about physics or soft matter that you think are interesting and worth debunking?
yeah, myths about physics. So I think most scientists are going to say something similar along the lines of, scientists aren't just egghead weirdos,
Hmm.
etc.
Hmm.
I think that's extra true, or maybe extra mythologized in physics, perhaps. Um,
Right. Yeah, for sure. People. Oh,
Big Bang
I see
Theory
that.
is definitely not helping, that kind of thing. As far as like the actual science it goes, I think maybe people will say physics, ooh, that's like string theory and, you
Mhm.
know, Einstein and all this stuff. That's just a small, small chunk of it. You don't have to be particularly good at, complex mathy type stuff to do physics. A lot of it is very similar to engineering. Um, and in fact, uh, I think it's like 50% or more physicists are basically interchangeable with engineers in the States, at least. Most of us are doing material properties. So we aren't always looking at space. We aren't always looking at stars or planets and things like this, or gravity and whatnot. A lot of
Right.
it is very practical. And
Yeah,
yeah, I think
I
a lot
think
of
that's
people
really
don't
important.
really, yeah.
So I mean, and you're quite evidently disproving that they're not all eggheads just by coming on. It is true though, I do see that sentiment at least from the outside, right? Is like, physics doesn't seem like people don't think it's applicable or like it's kind of out there, and there's like, yeah, exactly, Einstein kind of things. But all of the materials that we use, all the things that we're interacting with on a day-to-day basis, physics is really crucial towards every function of our lives. So there has to be people studying it.
Yeah, absolutely. There's so many physics questions that are still out there, that people are studying, that you can see, day to day. And if you have like a good intuition of like how things work, like if you play with things in the kitchen, a lot of soft matter, um, you can do demos that show complicated soft matter phenomenon in the kitchen. Like making a mousse is super complicated scientifically, but there's like lots of things you see every day that still need explaining, still need studying, and
Yeah, absolutely. And that's what you guys are doing.
yeah,
Brilliant,
in our own
right?
special way.
Yeah. Hey everybody, hope you're enjoying the first video podcast for Brain Buzz. Being our first episode, clearly we did a really shitty job with transitions, so here's our transition. The last half of the episode is going to be about Adam showing some demos, so showing what he's been doing with soft matter physics research. And then at the very end of the episode, you're going to see a tailored demo from Adam that's about 1.5 minutes long. It shows specifically what's going on within his work at the microfiber levels. So hope you're enjoying, and enjoy the rest of the show.
I can talk a little bit about some of the things that I brought. They kind of explain a little bit more about how material properties and size and shape affect the way that things deform when you put forces on them. So I started showing you the straw and the elastic band. I also talked about thin films, so we also do things with films. So where I said a fiber was something that's, very thin and very long. When we talk about films, we're talking about something that is basically a fiber but in 2D. So now it's long, tall, but still very thin. So paper is a great film. Skin counts as a film. This tensor band counts as a film.
An
but of
old
course,
school movie film.
Oh yeah.
Yeah.
That's actually probably pretty close to the
Yeah.
old $50 bill in terms
Oh,
of
look at you
material
flexing.
properties.
My goodness. Couldn't find any 10s or 20s, eh?
I have tens of these to my name.
Look at this guy with his physics grants.
But
Okay. Yeah.
and then also skin and like layers of fat and stuff. And of course, you would understand intuitively that these are going to behave differently. And so like an example, this is thinner than the tensor band and thinner than your skin. Can't really stretch this one, but you can bend it. And that's sort of the important point that we're trying to make here is that bending and stretching are different. So these are different modes of deformation, is what we would call it. But if you take a second and think about what's happening to the material when you bend or you stretch, there's not a lot different. So when you stretch something, if you look at its cross section or its thickness, every part of the tensor band is elongating at the same time and at the same rate. So that's just like an extension of the Hooke's law elastic band thing. We stretch this, and the whole thing is stretching in the same way. But once we get to films like this, we can do the same stretching. The area changes. But bending, what's happening is the top side stretches. So the top side has to get longer to accommodate this extra angle. The bottom side compresses, and the middle stays the same length.
Okay.
So where one thing is able to stretch, it means that the whole thickness cross section is able to stretch at the same rate, and it's happy to do that. But for bending, it's actually a little bit easier. You don't have to stretch it quite as much, and you actually get a compression. And so so now this thing here, if I were to try to stretch it, it's not going to be very happy to stretch because all of this area plus all of the thickness and everything has to extend at the same rate. If you bend it, then only the top bit has to do any kind of stretching at all. And it ends up being easier for this thing to do that kind of deformation.
Right.
Same idea for these elastic bands. and like the straw and everything. The material property itself, let's see, how do I say this? Something that is easy to stretch will generally be easy to bend, but it'll be harder to stretch it than it is to bend it.
Right.
For something that's very thin.
Okay. But then when you have the film that it gets longer, it's kind of dependent on the material. The bend is going to be different than the fold as well. Because with the tensor bandage, I mean, it's all about the materials that you're using, right? And that's in the end, like what you guys are kind of manipulating is what kind of materials or like, you know, materials is the best word I can think of. I'm trying to think of like the composition, whatever composes the actual object. That is what will depend on or will determine how it bends, how it folds, and how it stretches.
Yeah.
Yeah.
And then so that's sort of comparing the material itself, but then you can start playing with the geometry of it. So we have something that's very thin and it bends very easily. It might not stretch very easily. We can have something that is very soft now. And in this case, it doesn't really stretch very well. And it's also difficult to bend, but it's much softer than this would be.
Right. True. Yeah.
So yeah, its thickness matters quite a bit. And it turns out the importance of thickness for stretching versus bending, they're sort of different, similar to how like gravity was volume based and tension was area based. Bending and stretching have different dependence on the thickness of the thing.
Right.
Okay.
Is that an example would be when you have like you know, a piece of paper or whatever, and you what is it, fold it 8 times is the limit or something like that? Is that what it is? So as soon as you're doing that, then you realize the properties at which you can bend it or, you know, stretch it will change drastically, right?
Yeah, yeah.
Is it 8? Is it 8 folds? That's the amount that you can do. I'm trying to think. 3.
Funny you should ask that. I just interviewed a guy through this ComSciCon conference during the summer. I believe he just graduated from his PhD in basically hard condensed matter. But I asked him like what's the coolest Cycom experience you've had? And do you know Jay Ingram?
Yeah.
Sound familiar? Radio Lab, maybe? One of these podcasty guys.
Yep.
Yeah.
He actually worked on a physics problem for him for, I think, a book that he was writing. He asked this guy's supervisor, how many times can you fold, a sheet? Theoretical limit. What's the maximum number of folds you can do? And his supervisor was like, well, kind of busy. Roshan, do you want to do this problem? He's like, yeah, I'll give it a shot. So he's a hard condensed matter guy, so he is concerned with like the spacing between different atoms and things.
Okay.
But he tried to take it to the logical extreme of what's the thinnest type of paper we can have? It's going to be 1 atom thick.
Okay.
So if you bend the paper or the 1 atom thick paper, every time you bend it on that bend, the top bend part, you're basically stretching. Like we've said before, we're stretching the surface. And so the logical limit of bending a thing is going to be based on stretching the bonds between the atoms.
Okay.
So if you take this 1 atom thick thing, all these, chemical bonds or whatever, you bend it one time, you're going to stretch the bond at that top edge. You bend it again, it's thicker now, so the bend is going to be more extreme. The stretch is going to be more extreme.
Yeah.
And so you bend it again, or you fold it again, the stretch is going to get even more extreme. Keep stretching it, and I think he got to 18.
Wow.
But that's
With
a
1
piece
atom.
of paper that could never exist.
Right.
The hypothetical best sheet of paper.
Yeah, so I think if you do it right now with a piece of paper, you'll probably get somewhere around 7 to 8.
Okay.
What did you get? Were you just doing?
I got 6 with the sticky note, but
Okay.
it's not a proper. I think I got to 7 or 8 with like a regular sheet of paper.
Yeah. So the range is probably somewhere between 7 and 18. I mean, I've heard the number 11 before.
11. My goodness.
I
It
think that
has
was another calculation based on actual paper, but
it
less
has
than
to be
18 is what we can say.
it has to be in half, right? That's the deal. You can't just like fold it
Of course.
haphazardly.
Right.
Yeah.
6, 7. I think 7's the max for like my.
Yeah.
I don't know if I could do another. Yeah. Yeah. So 7, 6 or 7, depending on the piece of paper, I guess. Yeah. So 18 is the hypothetical max, you said.
Yeah, I'm not sure what atoms he was using, like what
Yeah.
bond length were you? Oh, was that 18? I think you just
Yeah, that was 18. Don't look
nice.
too close. I'll just kind of wave it at the camera.
Actually kind of looked like 18 and a half. I don't know.
Yeah, I mean,
Breaking new ground here. We'll get Guinness records on the line.
yeah.
Yeah, the other weird thing is you would think that like the area of the paper would affect it. Like if you had a really long one, 'cause
Right.
you could
Yeah.
like, fold it and then the way that it doubles, it's like geometrically that we cap out. It doesn't actually matter the area of it.
Right. So what you're saying more or less is like if you have a paper that's like your standard paper, if you were to increase it by like 10 times the size, you'd still be getting around 7 folds because of like the way it's folding with each other. So it doesn't matter how big it is.
Yeah.
That's interesting. Yeah, because I would have like being a dummy like me or just like not thinking too much about it, I'm like, yeah, just increase the size. It's all good. Like we can do more, like we can do 10, 12, no problem. But it's not the case. That's really interesting. And
Yeah,
that's all about the properties of how it folds.
there's a distinction to be made too, though. Depending on the size, it's going to take a different amount of force to do these folds.
Right.
Right.
So if you have like an infinitely large paper, the force is going to be way, way too big for you to even do like 3 folds or something.
Right.
But that's different from the paper failing and like tearing. And
Yes.
so when we say the total number of folds you can do, that's before the material
Breaks.
fails and breaks or something.
Yeah.
Right.
Because you can go and get like a hard press and like probably get an 8th fold, but it'll just rip the paper at some point.
Yeah.
Yeah. Interesting. That's really cool.
Cool.
I mean, that
Yeah.
was tangential, but I've really enjoyed learning a lot more about physics with you, Adam. This has been fun. I think is there anything else that you'd want to share with anybody that's kind of interested in physics or soft matter or anything that you're doing before we talk about your science communication work and what you've been doing from podcasting and your radio shows?
Yeah, I don't know. I would say just keep an open mind about physics, man. A lot of people, get sort of they shy away from physics, but it's not all math. A lot of it is material based. You can do a lot of it in the kitchen. There's actually this very popular first year course at Harvard where the lab components are just cooking. They work with chefs.
Oh, that's cool.
You can audit it for free as well. Maybe I have to send you the link to that, but
Cool. Yeah, for sure.
I mean that's physics right there. Anytime you're playing around with stuff, just I don't know. It's all around you. It's
Mhm.
not so bad. Um, I can maybe send you to some other like resources for people who want to do some experiments at home. There's DIYlab.net. No,
Okay.
.net.
We'll
Dot
figure out
org,
what it
yeah.
is and we'll include it with the material as well so they can go.
Yeah, but all sorts of resources online if you want to do some physics at home, do some fairly fun and basic experiments and just sort of see what physics experiments actually look like, what kind of questions you actually ask. Yeah, explore.
Yeah. No, I think
Great.
that's being inquisitive when it comes to the world around you is always something that you can benefit from, and that's exactly what physicists do, right? So, I was like physicists. Physicists.
Yeah, we can't edit that out now.
Yeah.
Awesome. Well, Adam, thanks for joining us for this episode of Brain Buzz.
Yeah,
Yeah,
this has been really fun. Yeah, thank you
Yeah.
so much.
my pleasure. That was a blast.
Great. Okay, so we'll wrap it up there. Follow us on or follow BrainBuzz on Spotify and Apple Podcasts. Subscribe to our newsletter, brainbuzzpodcast.com, and join us on Twitter, Instagram, and Facebook at BrainBuzzPod. Until
And
next time.
check our new website out. We're gonna have a new website up whenever this comes out too. So
Absolutely. Same location, brainbuzzpodcast.com.
absolutely.
All right. Until next time. Cheers.
Cheers.
Hi everybody, I'm Adam, and you're listening to me on the Brain Buzz podcast, and I promised you some demos. So, from the podcast, you probably know that I look at soft materials, and I look at how they deform when I apply different forces to them. So let's talk about the different types of deformations that we're going to see here. So, there's three basic ones that we're going to talk about, and here's an elastic band. We're going to use as a quick little demo. So there's stretching, there is bending, and there is twisting. And that's it. So if we want to get a little bit more technical, we can look at the schematic or cartoon I drew for you. On the left, we're stretching a beam, and on the right, we're looking at its cross-sectional area, or we're looking down the length of it. And when you stretch it, this whole cross-sectional area has to stretch as well. And now we can talk about bending, which is really just a combination of stretching and compressing. So if we bend something, the top half stretches, so that's the red bit I've shaded, and the bottom half of the object compresses, and that's the blue half. So then we can look at the cross-sectional area on the right again, and we can imagine that this middle black line is completely unstretched, and you get more and more stretching as you go up, and more compression as you go down. It might be surprising to think that, again, you can, break up the twisting action into different areas of stretching. So you twist, and the outside surface, or the skin, has to basically elongate and stretch. But as you can imagine, near the core of it, and if we look on the right side, this cross-sectional area, the core becomes less and less stretched as you go inwards. When we talk about the types of deformations that these things are going to undergo, a lot of it depends on geometry. And so by geometry, we mean size and shape. So this is long, thin, and flat. Alternatively, you could have things that are, sheet-like, thin, flat, but wide as well. You can also have things that are, like a rod or something. So it's thicker, long, still thin. And you can do the same sort of actions on these things, and depending on the geometry, you're going to get different results. And so all the same physics can describe things like what happens when a train track heats up and expands, or a root pops out of a seed and starts to grow, or even when a plant tendril grabs onto, say, a branch of another plant. In all of these cases, there's different types of compressions and stretching and growth that causes these objects to deform in unique and very interesting ways.
That's our first episode in the books. If you enjoyed what you heard or what you saw this time, please follow us on Twitter, Facebook, Instagram. Give us a share to all your friends. And please do follow us on Spotify and Apple Podcasts so you can see the newest and latest episodes that we publish every other Tuesday. Thanks again for listening, and until next time, cheers.